Welcome to our Quantum Deep Dive.
Great to be diving in.
Today we're diving headfirst into, a really fascinating intersection of two huge technologies, artificial intelligence and quantum computing.
Absolutely defining technologies for the future.
And specifically, we're going deep on a concept called hybrid classical quantum transfer learning. Our source material for this deep dive is a really insightful essay titled Hybrids Transferlernen. Quanten und klassische KI Vereint. It's by Jorgo Schneppert.
That's right. And based on Schneppert's work, our mission today is really to unpack what this hybrid approach actually is.
Yeah, why should you care? Why is it becoming important now?
Exactly, and what potential does it hold? We're sticking closely to the insights from his essay here.
Okay, so let's set the stage a bit. I mean, you've all seen the incredible stuff classical AI can do, right?
Oh, definitely. Machine learning, deep learning.
It's powering everything from medical diagnostics, autonomous vehicles, complex financial modeling. Classical AI is just fantastic at finding patterns, making predictions from huge data sets.
But, and this is a key but Schneppert raises, its power often demands massive amounts of data and frankly enormous computational resources. It's not cheap.
Right. And then you have the quantum world.
Yeah.
Which is just a completely different way of thinking about computation.
It's a fundamental shift, yeah. Instead of classical bits always 0 or 1, quantum computers use qubits.
Qubits. They can be 0, 1, or crucially both at the same time.
Yeah.
Superposition.
Exactly. Superposition and entanglement. These quantum phenomena allow for things like quantum parallelism.
Which means?
It holds the promise of exponential speedups for certain types of problems that just choke classical computers. Schneppert specifically mentions things like Grover's algorithm for search.
Or Shor's for factoring large numbers. Those are the classic examples you hear about.
They really showcase the potential, why people are so excited about quantum computing.
So, okay, putting AI and quantum together seems like the obvious next move, doesn't it? Quantum machine learning, QML.
It does seem logical. But Schneppert points out a really critical reality check here. Pure QML models, run entirely on quantum computers, face some serious hurdles today.
Like what?
Well, for starters, the quantum hardware itself is still pretty noisy.
Noisy.
Yeah, prone to errors. Plus, you have a limited number of stable qubits available, and honestly, the quantum algorithms for ML are still quite immature compared to classical ones.
Okay, so that naturally leads us where? If pure QML isn't quite ready for prime time.
It brings us straight to the motivation for a hybrid approach. This is Schneppert's core argument.
Because the current quantum hardware, it's good for some things, but maybe not a whole AI model start to finish.
Exactly. It's powerful for very specific tasks, but not ready for the whole shebang. So the hybrid model is, pragmatic. It's a way forward now.
Using classical computers for what they're good at.
Right. The heavy lifting, the stuff they do efficiently. And then you reserve the quantum computer for those specific, really hard subproblems where its unique abilities might offer an edge.
Even with today's noisy, smaller quantum computers.
Yes, even now. It's about finding that synergy today, rather than just waiting, potentially decades, for perfect, fault-tolerant quantum computers.
Okay, so that makes sense as the why. Let's unpack the what. What exactly is this hybrid, classical quantum transfer learning thing?
Okay. At its heart, Schneppert describes it as, intelligently blending classical machine learning techniques with methods rooted in quantum mechanics.
Merging the two worlds.
Precisely. The basic idea, like we said, is to get around the current limitations of both fields by combining their strengths. You use classical computing for the bulk work and bring in quantum for specific bottlenecks or tasks where quantum properties, like handling high-dimensional data differently, could really help.
And Schneppert actually lists some pretty interesting potential advantages. What are the main ones that jump out?
Well, what's really interesting is how it targets some of the persistent pain points in classical ML. Schneppert suggests this hybrid approach could potentially cut down the overall computational cost, maybe by offloading really demanding bits like certain optimization steps or linear algebra crunching to the quantum processor.
That'd be huge.
It could be. He also mentions more efficient ways to handle certain high-dimensional data types, maybe improving model generalization.
Meaning the model works better on new, unseen data.
Exactly. And even accelerating things like hyperparameter optimization, finding the best settings for your model, which classically can take ages and tons of compute power.
Wow. Yeah, if quantum can speed up even one of those, that's a significant advantage.
Definitely a win.
But, okay, bringing these two fundamentally different computing types together, it sounds incredibly complex. What does a typical hybrid model actually look like, architecture-wise, according to the essay?
Yeah, Schneepat outlined a sort of common structure you see. It usually kicks off with classical preprocessing.
Standard stuff. Cleaning data, getting it ready.
Exactly. Take your raw input, do the data cleaning, maybe some initial feature extraction, perhaps dimensionality reduction if the data's too big. All things classical machines are great at. That's your simput classical preprocessing step.
So prepping the data for the quantum step.
Precisely. Then, that nicely processed classical data gets fed into the quantum unit.
The quantum black box.
Well, not quite a black box. It's usually a specific quantum circuit designed for a task that might benefit from quantum weirdness, maybe complex feature mapping or pattern recognition or a specific optimization. That's the quantum circuit part.
Okay, and then what happens after the quantum magic?
The output from that quantum circuit, which might be classical data or quantum measurement results, gets passed back to a classical post-processing unit.
Back to the classical world.
Right. This unit interprets the results, maybe does some more classical processing, and turns it into the final output you want, the output.
So the flow is really input classical prep, quantum step, classical post-output.
That's the typical workflow Schneepat describes. It's really about that back-and-forth interaction, not one single machine doing it all.
So classical computing still does most of the, let's say, general work, but quantum tackles specific, maybe tricky calculations.
That's the idea. Schneepat clarifies, tasks like preparing massive data sets, storing them, training large pre-trained classical models, we'll get to that transfer learning bit, and interpreting the final output that usually stays classical.
And the quantum part.
That's reserved for tasks where quantum states or algorithms might offer something unique, like novel ways to encode classical data into quantum states using entanglement quantum feature encoding, or using quantum-assisted kernel methods, or running specific optimization steps with quantum algorithms.
You mentioned quantum kernel methods and quantum optimization. What kinds of specific quantum circuits are actually used in that quantum unit for these ML tasks?
Schneepat highlights two types that are frequently explored right now. One is quantum kernel methods.
How do they work, roughly?
They essentially use quantum states to map data into incredibly high-dimensional feature spaces implicitly. The hope is that in that huge space, patterns might become easier to separate, something that's hard classically.
Okay. And the other type?
The other common one is variational quantum circuits, or VQCs. These are really central to current hybrid approaches.
Why VQCs specifically?
Because they are parametric circuits. They have a fixed structure but contain adjustable knobs or parameters. And here's the hybrid part. Finding the best settings for those knobs, the optimization, is done using a classical optimization algorithm.
Running on a classical computer.
Yes. That classical optimizer interacts iteratively with the quantum hardware, executing the VQC. It tweaks the parameters, runs the circuit, gets a result, tweaks again. It's a tight classical quantum loop.
I see. So even tuning the quantum circuit is often a hybrid process itself with VQCs. Okay, now let's get to that transfer learning part of the name. How does transfer learning fit into this hybrid picture?
Right. This is where it gets particularly clever, especially given how limited current quantum computers are. Schneepat explains you can leverage classical models that have already been trained on enormous datasets.
Like using a pre-trained Google image model.
Exactly. Think of a deep classical neural network that's learned from millions of images. You can use that powerhouse for initial feature extraction on your new data. It pulls out really high-quality, meaningful features.
And those features are what get fed into the quantum part.
Precisely. Instead of feeding raw data into your small, noisy quantum circuit, you feed it these rich features extracted by the classical giant.
So you're essentially transferring the knowledge from the big classical model.
You got it. It lets the hybrid model benefit from all that prior learning without needing a huge data set or tons of time to train the quantum part from scratch, which just isn't feasible right now. Schneepat also mentions quantum-assisted feature extraction itself, where the quantum unit might help encode data in a way that highlights certain patterns better than classical methods alone.
That combination sounds really potent. Classical muscle for the big data stuff, quantum finesse for the tricky bits. Are there concrete examples from the essay where people are actually exploring these hybrid models today?
Yeah, Schneepat points to a few active areas. You see work in image and speech recognition.
Wow.
Like maybe features from a classical convolutional neural network, CNN, get passed to a small quantum layer for the final classification step.
Interesting. What else?
There's a lot of interest in optimization problems, especially in finance. using quantum approaches for things like complex portfolio balancing.
Makes sense. Optimization is hard.
It is. And also, in medical diagnostics, researchers are looking at things like quantum-assisted support vector machines, or SVMs. The idea is they might spot patterns in medical images, say, better than purely classical SVMs could.
This all sounds incredibly promising. Like it could unlock new AI capabilities, but what's the reality check? How hard is it to actually build and run these things right now?
Yes. That's where Schnepphat brings us firmly back down to earth. There are significant practical challenges.
Despite having software tools.
Right. Even though we have frameworks like IBM's Qiskit, Google's Cirq, Xanadu's Penny Lane, which are designed to help build these hybrid models, the underlying hardware is the big bottleneck.
Okay, what are the main hardware headaches?
Schnepphat is very clear on this. Number one, current qubits are noisy.
We talked about noise. Errors, basically.
Yeah, errors stemming from quantum noise itself, but also decoherence, the quantum state just falling apart too quickly because of the environment, and gate errors, the quantum operations aren't perfectly accurate.
So the results aren't always reliable.
Not perfectly, especially for longer computations. Then there's the simple fact that we just don't have that many stable qubits available on current machines. For complex problems, you need more.
Okay, what else?
He also notes that sometimes the actual computation time on current quantum hardware can still be slower than doing it classically, counterintuitively. And maybe the biggest practical hurdle is just the sheer technical difficulty of smoothly integrating the classical and quantum hardware and software stacks. Making them talk to each other efficiently is non-trivial.
So the potential is massive, but the hardware limitations, the noise, the scale, the integration, that's the main break right now.
Absolutely. Schnepphat really emphasizes that a lot of ongoing R&D is needed. We need better quantum algorithms designed for this noisy, intermediate-scale quantum NISQ era we're in, and much better ways to integrate everything into practical workflows.
But looking ahead, beyond today's NISQ challenges, what are the potential breakthroughs that could really make these hybrid systems, game-changing?
Well, the development of more powerful quantum algorithms specifically designed for machine learning is a huge area. As the hardware gets better, less noisy, more qubits, these algorithms could potentially unlock capabilities we just can't simulate classically today.
And the long-term vision?
The long-term vision, as Schnepphat lays it out, is really the successful integration of these hybrid systems into real-world commercial applications across tons of industries.
Right.
Imagine the impact in medicine, maybe dramatically speeding up drug discovery, or finding new materials in energy, detecting really sophisticated fraud in finance, or even developing unbreakable encryption in cybersecurity. The potential applications are vast.
Okay, so let's try to quickly summarize the key takeaways from this deep dive, based on Schnepphat's essay.
I think, in essence, Schnepphat presents this hybrid classical quantum transfer learning as a really significant and very active area of research. It's driven by practical necessity right now.
It's about strategically combining the best of both worlds.
Exactly. Combine the established power and scalability of classical AI with the still nascent but potentially exponential power of quantum computing.
And the goal?
The core goal is to use the strengths of each to sidestep the weaknesses of both, ultimately paving the way to maybe tackle problems that are currently just too hard for either classical or quantum computers on their own.
Okay, so here's a provocative thought for you, the listener, to chew on after this. As these hybrid systems keep improving, and as quantum hardware slowly matures, will they just end up being, slightly better tools for the kinds of AI tasks we already do? Or could they fundamentally change the kinds of questions AI can even address, opening up entirely new frontiers for computation and maybe even scientific discovery?
That really is the billion-dollar question, isn't it? And the answer probably depends heavily on how quickly both the quantum hardware and these clever hybrid algorithms continue to evolve.
And we should remember, all of this discussion was sparked by the insightful essay Hybrids Transfer Lernen, Quantenklassische KI vereint by Jürgen Schnepphat. Really appreciate the foundation he provided.
Agreed. It was an excellent basis for this deep dive.
Well, thank you for joining us for this quantum deep dive.
Goodbye, everyone.